In today's video I would like to discuss this ventilator that I've been building over the past 3 months. I'd like to show you all of the parts that go into it, how they all work together, and I'd like to discuss some of the design choices that I've made in building this device. I'd then like to discuss some of the improvements that must still be made to make this device safe and effective. Before I get into that though, I would first like to discuss 2 preliminary questions. First, is a device like this even necessary? I strongly fear that it might be. The coronavirus pandemic is mostly under control here in Europe, but that's the result of quite strong measures that have been taken in the past, and then some of those are still in effect today. If those measures are lifted before a vaccine is widely deployed, then the virus could just resume its spread, which is a situation that we can already see happening in the United States. An even bigger risk, perhaps, lies in lower and middle income countries. In these countries, people cannot afford to do social distancing or a lockdown. If these people don't work for a day, then they don't get to eat. The consequences of that grim reality are already visible in Brazil and in India. The second question is, why build an entirely new design like this? Why not just ramp up the production of an existing design? You can't, and it has to do with the economics of ventilators. Ventilators are built primarily for the rich Western market, and they obviously do a very important job. Because of this, the primary driver in the design is safety and performance, with cost very far below those two. As a result of this, the ventilators that you can buy typically cost between $30,000 and $50,000. The flip side of this is that ventilators are usually constructed out of custom bespoke components, because that's what gives you the best performance. However, if you try to ramp up production, you run into the issue that the parts simply aren't there. Remember when Medtronic open sourced their PV560 ventilator? None of them were built. None. The parts to do it simply don't exist. The challenge before us then is to build a ventilator out of commonly available components. Components that you can buy in at least tens of thousands of quantity. It would also be very nice if the ventilator is affordable, especially again looking at lower and middle income countries. Such a device is what I intend to show you today. Starting at the front, we have the color touchscreen over here, and we have the fake test lung here. Now this is a bit improvised because the actual test lung that I ordered got lost in post. And the screen. So everything is controlled via the screen, and the reason that I'm using this one here is because I'm using a Raspberry Pi on the inside, so it's simply a matter of connecting the HDMI and the USB, and then the touchscreen works. I do think you want to use some kind of a color screen, because you want to show graphs of pressure, volume and flow versus time. Though you could opt to use not a touchscreen, but to control the unit with knobs and buttons instead. Looking a little bit further down, we have the gas inputs and outputs. So from left to right, we have the gas coming out of the machine and going into the patient. To the right of that, we have the air returning from the patient going back into the device. And this is necessary so that the ventilator can control when the patient is allowed to exhale. Here we have a small little exit for the air from the patient to finally leave the system. And then on the right here we have 2 ports for oxygen and air, and these will be mixed in the appropriate ratio inside the device to deliver the mixed gas to the patient. Looking at the unit from the side now, here we have the power input, so currently I'm supplying it with 230 volts AC. And then looking inside of the unit, we can see 3 different sections to the device. So up here we have all of the electronics. In the back here we have the pump module driven by the stepper motors. And this pump module gives the force required to move the gases around to the right places. And then on the lower level here we have the valves and the tubes that direct the gas to go into the right place at the right time. With the top plate removed, we can see the four major components of the electronics section. We have the power supply, which takes the 230 volts AC and turns it into 24 volts DC. This is a meanwhile unit that can also accept 110 volts, like most units can. We have a backup battery over here, so that if the power is interrupted, the unit will still function. We have the Raspberry Pi here, which controls everything. And behind here we have a custom interface board, which takes all of the readings from the sensors and routes that into the Raspberry Pi. And then it takes the decisions made by the Raspberry Pi and translates that into motion of the motors here and the valves opening and closing. I've now removed the electronics section so that we can get a better look at the tubing and the valves below. So starting here on the right, we have the oxygen and air inputs solenoid valves. And these two lines come together in this T-piece, and then they go through the one-way check valve into the bellows pump. And then from the bellows pump we go through the other check valve via these angles into the inspiratory solenoid valve, and then through the T-piece out of the machine and into the patient. And then from the patient it returns through the other line, and then it just goes through this solenoid valve over here and the air comes out. So what would a cycle look like? Well, to start the inspiration, you open up this valve so that the air from the bellows can actually make its way into the patient. You have this valve closed to ensure that whatever air you push into the patient doesn't immediately come back out again. In that case, this would basically just be a leak and you're pushing air right out of the system here. And both of these valves for the inputs can be closed. So the way you start is by turning the bellows pump like this. So both of these stepper motors go at it. And that is basically an inspiration. So you can do this either in a volume targeted mode. In that case you can basically calculate how far you have to compress here. But I think with a PID loop or similar control loop, you can also do this with a pressure targeted mode. Whatever the case, once you reach the end of inspiration, you have to close the inspiratory valve and open the expiratory valve. And once you start doing that, the patient will start exhaling, and simultaneously the bellows pump will start to turn back. So what you do is you open the oxygen valve and you move the bellows back part of the way. And then you close the oxygen valve and you open the air valve, and then you move the piston up the rest of the way. And then by changing the distance with the oxygen valve open versus the distance with the air valve open, you can precisely control the concentration of oxygen that you deliver to the patient's lungs. The exhaust valve is initially open so that the patient can start to exhale. And then at the right time you have to close the PEEP valve or the exhaust valve again to maintain the correct level of PEEP, the correct level of pressure inside the patient's lungs. There must also always be an amount of positive pressure inside the patient's lungs, and you can achieve that by closing this valve at the correct time. So that is essentially how a cycle is supposed to work. And let's take a little closer look at the pump. And just for those who haven't seen it, this is the piston pump that I initially was using. So this was driven by a motor mounted here with a rack and pinion, and then that piston would go like that. So that's what I started out with, but for the piston pumps I could never really get the seal to work properly while also not having an incredible amount of friction, so I never really got the pistons to work. So here's the pump module lifted out of the machine, and the way this works is you have two stepper motors, and then using these semi-rigid couplers, they drive these TR 8x8 lead screws, and then using the nuts here on this little cross member, it moves the bellows up and down essentially. So again, if you rotate on the couplers here, the thing moves. So looking in particular at the bellows, I have here essentially the new generation. So this is what I want to install in the pump module shortly. So what you essentially have is a top plate, a bottom plate. You have clamp rings on both ends. So these are just hose clamps essentially, but they're 3D printed. And then between those two ends you have this 3D printed bellows. So these bellows are made out of Ninja Tech Cheetah, which is a thermoplastic urethane. And so you can compress these like this. And so the difference between this bellows over here and this one here is that this one has a wall thickness of 0.9 millimeters, and this one is doubled up. This has 1.8 millimeters thickness on the walls. So I'm expecting this to be a little bit more durable. I'm also expecting to receive a medical grade bellows, a commercial one. So that of course would be a lot better. It does have a little different dimensions though, so I should probably change out the pump module as well at that time. One final thing I should point out on the bottom here is this inhale and exhaust manifold essentially. So that's a lot like this bottom plate, except it's a whole lot thicker, which allows for these two hose barbs to come out. And these hose barbs are of course connected via these legs into the body of the bellows itself. One other thing about these bellows is that you have these two NEMA 17 stepper motors, and those two together are a little bit marginal. And the other issue is that if one of them were to fail, or if one of their drivers were to fail, then the entire device would come to a halt. So what I'd like to do instead is have a single NEMA 23 motor. I want to have it somewhere like this, and then it'll have a gear on the shaft, and that gear will drive two gears which are connected to the TR8 lead screws. The other advantage to that is that it's then mechanically impossible for the two to ever come out of sync. And one of the other nice things then is that you can also start using a beefier stepper driver, which might be a little bit cooler in the end. I'm currently using these small step stick drivers, and they get really, really hot. And I'm not sure if that's great for their longevity. Now that we've seen all the valves and the motors in the machine, I'd like to go back to this electronics board and show you what's happening. So here we have 4 outputs, and each of these controls a single solenoid valve, and these are driven by a single N-channel MOSFET each, which are hidden behind this ribbon cable. The ribbon cable is what connects the Raspberry Pi with all the brains in it with the interfacing board. Down here we have 2 stepper motor drivers, and using these cables they are connected to the stepper motors. We have the 24 volt input, and the 24 volt comes from the battery and from the power supply. Input stabilization, we have a small converter. This converts 24 volts to 5 volts, and the 5 volts is what powers the Raspberry Pi. And so to minimize resistance, the power to the Pi is delivered both via a USB cable and via 2 connections in this 40-pin header. And finally, down below here we have the BMP388 pressure sensor. So this sensor measures the pressure in the ambient air. And then there's a second BMP388 sensor in this box down here, which we've seen before. And so what the machine does is it measures the absolute pressure of the air just around itself and the absolute pressure of the air inside of the system. And the difference between those two is the gauge pressure, or is the excess pressure in the patient's lungs. all of the pressures that you generally talk about when it comes to ventilation are gauge pressures. Now, I do think that it's more convenient to use one of the MPX pressure sensors rather than using a set of BMP388s. It doesn't matter so much accuracy-wise, but it is probably more convenient. The final thing I want to point out, silly as it may sound, is this little capacitor here, which stabilizes the rails for the stepper motor drivers. That might sound optional, but having blown up 2 of these now, I can tell you it's not optional. You do need to provide a capacitor close to the stepper drivers to make sure that it don't blow up due to inductive spikes. The final thing I'd like to show you about this device is the battery backup in action. So with this switch over here, I can disable the main power. As you can see, that does nothing. And just to prove it to you, there's no mains connection now, and the device is still running completely normal. So this is now all under battery power. And then we can re-enable power, so we plug it back in. Enable the switch. And it's still running. Now the batteries are charging back up, and the device hasn't noticed any interruption. Now that we've seen where the device is currently, let's go over the very long list of things that still need to happen to make it a viable device. The first thing I want to talk about is the oxygen input. So I've described how the oxygen and the air can be mixed inside of the bellows to provide the right oxygen concentration. But one of the things that's quite notably missing is a concentration sensor to verify that what you're asking for is what you're getting. The other thing is that the oxygen should be supplied at around atmospheric pressure, perhaps just a little bit higher. And you'd like to have a sensor on the input end where the oxygen and air meet at that T-piece, a pressure sensor to verify that the pressure is not outside of any limits. On the oxygen concentration, you also have to ensure that all the components that touch the gas are oxygen compatible, and the tubes and fittings, I believe, are. But the valves are not. So the valves have aluminium bodies, and those need to be changed out for valves with brass bodies. So I'm looking at brass body semi-direct valves. I'm hoping those are going to work. The other thing is for the bellows pump, we're getting the medical grade bellows, so those should be compatible. The hose clamps do not contact the gas, so that's fine too. So it's the end caps that need to be made probably out of brass. And then on this side here, on the output manifold, you need to figure out something to do that in brass or something else that's oxygen compatible, because PLA almost certainly isn't. Once that's all done, of course, then there's also the kind of obvious thing that you have to test the device, run it with increased oxygen concentrations, and check that you, first of all, can deliver variable oxygen concentrations, and second, test that the thing doesn't set itself on fire, because that's kind of a big risk with increased oxygen. The other big theme is the electronics, and there's a lot to do here. So one of the things that is most notably absent on this unit is a flow sensor. So I have a flow sensor here. So this is the AWM 720P1, yes. And this thing is a very good flow sensor, but it is based on hot wires. And this thing costs around and about 200 euros. It's a bit cheaper perhaps if you get it from better places. But you want either one flow sensor bidirectional here, close to the patient, or you want one on both the inspiratory and the expiratory limb. Now, if you put it here, it's going to get contaminated with COVID and you're going to have to throw it away. The other option, if you put them inside here, you need one on inspiratory and expiratory, so you need two of them. And with flow sensors at 200 a pop, both of those options aren't great. So I'm looking at getting a Venturi-based flow sensor, but currently I haven't yet gotten any success in getting one of those, but that is in the cards still. The other thing I've discussed already is the BMP388 pressure sensors. Those are good, but you do need to make that little box at every place that you want to have a pressure sensor. So I'm looking at using differential pressure sensors, specifically the MPX 5010. And the other advantage is, because those are differential pressure sensors, they inherently work well with Venturi-based flow sensors. When we're looking inside of the machine, you could see my work on the perf board with all the components scattered around and my beautiful soldering work. That of course does make sense because it's still kind of a conceptual device, or at least it was. But we've now got a basic idea of what we want, what kind of devices we need. So I think we're now also at a point where we should look at getting a proper board design and a proper schematic. You don't want to spin that up if you're still not sure as to how your device is actually going to work, but we're now at the point that we want to do that. Looking at the software running all of this, right now I'm running Python on top of Linux on the Raspberry Pi. And that is a whole stack of things that aren't great. So using Python, being an interpreted language, obviously isn't fantastic to start with. And it being run on Linux is also not a great idea, because Linux is not a real-time operating system. So if you want something to happen within a certain time frame and you want that to be guaranteed, Linux doesn't provide that. Now in practical terms, it has never failed on me, but this being what it is, you do want to have more guarantee essentially. You want more guarantee than, well, I never saw it fail. On the software as well, there is a lot to be done. There are two things to be done, the patient trigger and the alarms. And the first thing I want to show you is the patient trigger. Now zoomed in on the screen so you can see the reading on the pressure here. So I'm going to take this tube and suck on it a slight bit. And so you see a pressure of about -6, -7 centimeters of water. And this negative pressure is very clearly outside of the noise floor here, outside of the noise. So it's quite easy to detect based on a simple threshold. And if you detect such a negative pressure, you would then trigger the pump to deliver a breath. Now, that negative pressure, is that something that you can reasonably do as a patient? So I'm a healthy guy, not suffering currently from COVID. So what I can produce is this. So that's -110, briefly up into -120, and going into the other direction, roughly the same, maybe a little less. So producing just a couple centimeters of water just to get outside of that noise floor is pretty easy. The final points on the software is first the alarms. So currently none of the alarms are implemented, and one of the example alarms, for example, is if you were to activate the pump and you do not measure the pressure increasing, but you do measure a flow, for example. That means that there is air leaving the system, but it's not going into the patient, it's just going straight out. That means that there is a leak or a disconnect in the hose. Alternatively, for example, if the pump moves, or at least you give the steppers the command to move, but you get no flow and no pressure, that would mean that there's a problem in the pump itself. There's a couple more alarms like that, and those still need to be implemented. That is again a software thing, you don't need dedicated hardware to do that. And finally, what I mentioned before is the reason you want one of these color screens is because you want to provide live updating graphs of the pressure, flow and volume, because that allows a physician or a nurse to have some idea or to get an idea of how a patient's lungs are doing. For example, if you're applying a relatively high pressure but you're not getting that much volume in a pressure targeted mode, you would then conclude that the patient has very stiff, very non-compliant lungs. There's obviously a lot more to it. I'm obviously not a physician, but that's the kind of things that people trained in the business can do with those graphs. And it's another one of those very important things to give people really the best chance to survive this disease, rather helping doctors help patients. That's really what that's about. There's a couple of other things that should still be added to this device. The first is a humidification unit. The issue is that the oxygen that you get from a bottle or anywhere else usually is bone dry. There's no moisture in there. And if you use a pressurized air source for the air, because that's arguably cleaner, then that would usually be completely dry as well. Now if you breathe normally, like I am now, then the air that you breathe in is a little bit humid to begin with, and then once it passes through your nose cavities or your mouth, it picks up a little bit of heat and humidity there before it gets into your lungs. Now if you have an endotracheal tube down your throat, you don't have that either. You just have the air going through that tube, bypassing that exchange of moisture entirely. So if you weren't doing anything about that, you would get extremely dry air directly into your lungs, and that basically dries out your lungs, which is a very bad idea. So what you want to do is add a small little unit that introduces moisture into this pathway. The other thing is a fairly simple thing, is an overpressure release valve, which this thing currently doesn't have. So if for any reason at any point the pressure goes above 60 to 80 centimeters of water, that should be blown off immediately. If you go above that, you risk inflicting acute barotrauma on your patient, which basically means that you're severely injuring his lungs by blowing them up. If you're already suffering from COVID, that's really not a great outlook. The final thing, which I've already briefly mentioned before, is I have these two small-ish motors driving the pump module, and I'd like to replace that with a single motor, also because I'm noticing now that the stepper motor drivers for these things are not really happy being under this plate. They are getting really quite hot, and that's really not a great thing. I hope you found all of that interesting and informative. If you'd like to hop on board with this project, you can do so at airtoall.org. All of what we're doing here is open source, so I will leave a link down below to the appropriate GitHub page as well. I do have to say that this particular unit I basically put together without modeling it in CAD. I previously, of course, had this piston pump, and I built an entire unit around this piston pump, and that is also what you can see on the GitHub, but this entire unit failed because this pump failed. The other group you might want to check out is the one of the winners of the EU versus Virus Hackathon, which is OpenVent. I'll leave a link to those in the description as well. With that, I'd like to thank you once again for watching. Have a great night. Don't forget to hit one of those buttons on your way out.